Okay, welcome everyone back, and we're starting with a talk by Paul Willey from Lancaster University and EBTC. Paul, welcome.
Well, thank you very much for inviting me. I think I'm the token Brit. Can you guys hear me okay? I can't tell if I'm being amplified. Yep, okay, good. So, I hope you've got a coffee. I've got a sonorous voice. I've got one so I stay awake through my own presentation. I was asked to talk about practical challenges in assessing indirectness and the implications for integrating multiple streams of evidence in systematic reviews. I'm a researcher based, for those of you who haven't yet had the dubious pleasure, I'm a researcher at Lancaster University in the evidence-based toxicology collaboration at Johns Hopkins Bloomberg School of Public Health. I edit systematic reviews for Environment International. I think I'm nudging somewhere in just getting up to 200 systematic reviews edited now. So I kind of seen a lot. It's kind of my cold, dead stare, I think. My research is around systematic review methods for environmental health research, and I particularly focus on frameworks for systematic evidence surveillance and synthesis, so the rules for combining lots of individual studies into meta-studies. Critical appraisal tools, so distinguishing like good systematic reviews from maybe ones that aren't quite so reliable. High quality primary studies for maybe primary research isn't quite so reliable. Research standards, particularly around best practice in conduct systematic review. I also do quite a lot of work on quality assurance and control in the publication systematic review. So making sure that when, as a journal, we publish systematic review, you as a reader can be fairly confident that it's a pretty good one. So today I'm going to touch on a number of different themes. They've already been picked up this morning by different speakers. So I'm kind of pleased I won't have to explain like a lot of this stuff again in a way that's definitely worse than how the other speakers presented it already. I'm going to be talking a bit about systematic review as a grounded approach to evidence synthesis. I'm going to present a Pico-based framework for assessing the external validity of studies. That's kind of a little work in progress. I'm very interested and excited to hear how you guys might react to that. I'm going to present some preliminary empirical evidence that successfully grounding systematic review methods is actually extremely challenging, and we should be very cautious about our prospects for success in that space, and how that, in combination with the Pico framework that we present, anticipates a computational approach to systematic review. And then I'm going to describe maybe the kind of pathway that we need to follow in order to develop successful grounded computational methods to get computers to do systematic reviews for us. So, quick recap. So, systematic review. I just define this myself as a research project which tests a hypothesis using pre-existing evidence instead of conducting a novel experiment. By which I mean, you might be thinking about, you have a research question, you might be thinking that you want to spend lots and lots of money on like a great big rat study which will provide a definitive answer, or a clinical trial, or a great big observational study, but that might take like 10 years to do. It might be unethical if we already know the answer, so you're going to go and see if the existing studies which have already been published provide a satisfactory answer to your research question, so you don't have to go and do the primary study yourself. Right, we have a bunch of measures that we introduce to make sure that when we do that kind of evidence synthesis and systematic review, that we minimize risk of bias in that process relating to searching and screening the evidence and assessing the quality of the studies. So bias from individual studies isn't transmitted through to the findings of your systematic review, and like decent statistical methods and so on and so forth. Okay, so I hope that's familiar to you guys. I talk a little bit about systematic review being advanced on traditional narrative methods because it uses discussable explicit methods to ground the test of the hypothesis. So what do you mean by that? Well, what we're dealing with in a systematic review is trying to find the textual record, which is our evidence of what was happening in all these studies that we're including to test our hypothesis, with evidence that those things that we're finding out about in those individual included studies matter for understanding how reliable they are in terms of answering that question that we've got, right? It's a little bit of an abstract concept. I'm like an ex-philosopher of science and things, it kind of shows sometimes. So we have our systematic review hypothesis up over here. Then we kind of do lots of work aggregating the textual record of existing studies which are relevant to testing that hypothesis through our search and selection strategy. And that gives us like a big bag of textual records of all the studies that are relevant to that question. Okay, each of those studies asks its own hypothesis. We're not necessarily so interested in what the hypothesis the individual included studies were. What we really want to know about are the procedures and the observations that are relevant to testing our research question, or testing our hypothesis. So we suck all that data out, And then once we've got all that in a database, we appraise the quality of that evidence. So we look at the risk of bias. We look at how relevant that evidence is to answering the question that we've got. And then we kind of smoosh that all up in our evidence integration process to determine the extent to which existing evidence provides us with an answer to that question that we've got. So the current approaches to evidence integration, they're based on a concept of dividing evidence into streams or lines, right? So EFSA uses the term lines. I think I heard lines somewhere else. NTP and EPA use streams. Evidence is synthesized within each stream. So you kind of synthesize the rat studies over here, and you synthesize the human studies over here, and you determine the certainty in the results of each of those individual systematic reviews. And then the integration is a function of combined certainty across those streams, right? So we generate a judgment of the overall level of evidence in the answer to that research question that we had. Now, when it comes to actually doing a systematic review, there are particularly one in support of maybe some of the more complex analyses that we have in chemical risk assessment, where we're trying to understand, say, a quantitative relationship between an exposure and a health outcome in a target population. It's not clear that the methods that were developed for supporting hazard classification, which is what NTP was doing, and Andy may wish to correct me on this, was NTP was proposing back in 2014 when these methods were published. It's not clear how easily those apply to these more complex analysis objectives that we have, perhaps in other risk assessment contexts. It's also, we do already make decisions about which studies we include in our systematic review and how we divide these evidence up into streams based on mechanistic data anyway. So we might decide that, say, like this kind of, say, Wistar rat model for a particular exposure is not really relevant to the human, to understanding human health risks. That would be a decision made on mechanistic evidence, but we're using that information in terms of like parameterizing our review. We're not actually like necessarily integrating that information late in the process. It's like setting it up. And then we kind of have this difficult job of trying to understand how these two different streams that have been analyzed differently kind of meet up in the middle, kind of at the end of an analysis process. And of course, we're also conducting mechanistic studies because they describe or predict health outcomes in particular populations. So the rationale for like streaming evidence or deciding where the joins are in the evidence space aren't necessarily entirely clear what the reason for that is. So there might be more we can do to systematically incorporate mechanistic evidence into systematic reviews of exposures. So you've got this Pico-based framework for evidence integration, which I think may give us an opportunity for thinking about, or rethinking, in fact, how we stream evidence by suggesting we don't need to stream it at all, in fact. So we have a systematic review, which is a test of a hypothesis using existing evidence. And when we do a systematic review, we interpret our hypothesis as a research question, which we formulate as a population exposure comparator outcome statement. Then a common scenario that we're faced with in environmental health research is having a suspected relationship between an exposure and an outcome, but that relationship's unknown, right? So this is one of the scenarios in a recent paper by Rebecca Morgan and colleagues, which I was a co-author on, where we laid out 5 different kind of case studies for thinking about how to develop Pico statements of different research scenarios. So we consider like this Pico. We might be thinking about the effect of organochlorine exposure on endometriosis risk in women. So we'd say among adult females, what is the effect of 1 mg per kg body weight childhood organochlorine levels in blood versus 1 mg per kg body weight incremental increase on endometriosis? I kind of made this up, so if it's not quite like mechanistically correct, I have to apologize for that. I just do the frameworks. Now, when we think about doing a systematic review, if we had really strong evidence from human populations, right, we might not need to think about including indirect evidence from mice and rats and mechanistic studies, right, because we already think we know what the answer is. But we might want to think about might want to understand the mechanism by which, say, organochlorines have this effect. Or we might not have very certain evidence from humans, in which case we're going to want to expand our horizons, if you like, for our what we would count as admissible evidence or includable evidence in our systematic review. So in that circumstance, and it's a common one, obviously, in risk assessment, we'll look at intermediate outcomes, so markers of disease. We might look at animal models, which we think are relevant to the human health context. We might look at similar chemicals for read-across analysis. And all this indirect evidence is relevant to answering the question and could increase certainty in a test for hypothesis, We just need to think about how relevant it is, if you like. And there are lots of ways of organizing this evidence. A recent example, which is kind of like fairly intuitively developed, and I don't want to come across like I'm criticizing these guys for doing the research the way they did, because they weren't thinking about trying to solve this problem. They were thinking about organochlorine exposures and endometriosis risk factors. It's just interesting to see in this protocol that we publish in our journal that we've got a number of ways of kind of slicing up the evidence which aren't really like streams and are more responsive to particular characteristics of classes of study in the evidence base. So I don't know if you can see this, but they think about primary apical outcomes and intermediary secondary outcomes. They're thinking about things like spontaneous endometriosis, and then in an assay for that, it might be in vivo onset of endometriosis after chronic exposure in non-human primates, for example. So that's one kind of group they're interested in. And they might be thinking about sort of migration or attachment of endometriotic tissue. So that might be experiments evaluating the invasiveness of implants in rodents or primates. And it's quite informally presented in this table. So you can probably start thinking about, well, can we interpret this into Pico statements, right? Because that's what we build our systematic review around. So you've got a systematic review, and the model that these guys are effectively proposing is that we break down our systematic review target Pico, if you will, into a load of sub-Picos, and we test each of those individually. So we have like non-human primate with chronic exposure in their table. The comparator wasn't necessarily totally clear, and they're thinking about spontaneous endometriosis. We've got like a rodent model, which is chronically exposed with proliferation of endometriotic tissue. There are some in vivo and in vitro models. As described, the hypotheses under test and the relevant Picos are actually quite ambiguous. So if we were doing a systematic review, we'd want these to be much more tightly defined. But in fact, there's a question, of course, of whether or not it's actually worth doing this, because there could be like hundreds of these statements potentially. But like any study design you could think of that could test this endometriosis organochlorine exposure effect relationship, you could come up with literally any experiment for that. And then you'd be thinking, well, if we're kind of running 100 Picos to test this one systematic review, that's not only cumbersome, we're probably at risk of p-hacking our way through to kind of spurious findings, just because one of those analyses is going to come up true, right? Or we'll just end up with loads and loads of tests for spaces in which we don't have any evidence, okay? So it might just be easier to just observe how direct the evidence is. So how do we do that? Well, I would propose that we can use Picos as kind of like a directness framework or framework for external validity. So we can say that relative to the Pico, which is the target of a systematic review, we assume that, to some extent, all evidence is indirect, and you can therefore break it down or evaluate it in the following way. So we'll define our target Pico, so we'll call that the T-Pico for systematic review, which we do already, so we should be familiar with that. And then we can extract the experimental Pico, so our E-Pico, from each individual study that we include in our systematic review. Now, not all studies or primary studies will use a Pico formulation to state their objectives, but we will be able to extract implied Picos from these individual studies because they mirror the structure of a systematic review. Then we can evaluate the similarity of each E-Pico to the systematic review T-Pico, and then we can describe directness of the evidence overall as a function of how the aggregate of E-Picos map onto our T-Pico, right? How does that work in practice? Well, we just basically stick the stuff into a matrix or a table, right? So we can have our target question, which is the one in yellow along the top, and then we break down the characteristics of each of the included studies according to population features, exposure features, comparative features, and outcome features. So here I've just done a fairly arbitrary kind of back of the napkin breakdown into, if I can count, 1, 2, 3, 4, 5, 6, 7, 8, 8 features, 9 features, 9 features, right? It just gives us a structure for like classifying how similar, in a way, each of those included studies is along a set of predefined dimensions, basically, which we like to do in systematic reviews, right? And we could allow us to describe all types of study design using the same set of categories, and it doesn't matter if it's an in vitro study or a human epi study or a rat study or whatever. And in theory, we can make comparisons between experimental Picos then and our target question without having to divide the evidence up into streams beforehand. We just look at it and we see how similar it is, right? And we can make explicit the information that we're interpreting, so these study features, even if we don't yet know the rules for interpretation, which are just flagging some of the computational stuff we go into a bit later. So we can judge similarity at the level of whole study if we want to be very low resolution. And the moderate resolution, we might do it just at population or exposure or comparator outcome, or we might do it at the level of individual Pico sub-element. I suspect it would be the level of individual Pico sub-element, which would be important because these are really, really important characteristics that we're hearing this morning for determining whether or not an animal study is going to be predictive of human health outcomes, or we should be including an in vitro study in our systematic review or whatever, right? The question is how we ensure that our judgments about study similarity are valid, and that's where things get difficult. I'm not going to propose an answer to this. I'm just going to flag that there are a couple of powerful intuitions which are driving the AOP approach to understanding this. So if we've got an observed intermediate event, so like a biomarker, which we know is strongly predictive of a target outcome, or which I mean we're pretty certain or very certain is predictive of a target outcome, that's going to make us feel like that evidence is less indirect, right? So we might have an in vitro assay, or we might be observing a biomarker of an event in people, an observational study. If we know that very observable biomarker is a really good predictor of a less observable, directly relevant outcome, we're going to be thinking of that as more relevant to our research question than it is less. And if we've got this commonality of mechanisms between two different populations, so if we are pretty confident that the mechanism we're seeing in this rat model is the same mechanism that's happening in people, then we're going to be feel better about saying that our rat model is more directly relevant to people than it would be otherwise, right? If that's true, then maybe a judgment of similarity or directness can be derived from a function of certainty in an AOP network, and that gives us potential for grounding judgments of directness in existing biological knowledge, so long as that knowledge is gathered systematically. Because it's no good saying that we're going to ground our understanding of, or ground our judgments of AOPs for the purpose of doing grounded systematic analysis if the AOPs themselves haven't developed systematically in a grounded fashion. So, practical challenges in achieving grounded analysis. I have no timer on here, by the way. Do we know how long I've been going on for? I've got 5 minutes left. Okay, excellent. So, two major practical threats to grounded systematic review. We've got implementing valid processes and overwhelming data volume. Right, so at Environments International, we've been collecting pre-publication data on the systematic reviews we've been receiving for the last year and a bit. So we assess the quality at point of editorial triage of the systematic reviews we receive, and if they make basic fundamental errors, then we reject them. And we catalog, we note which basic errors are being made when we make this rejection decision. Okay, so I won't go into all the detail, but 80% of the time we see that the submissions use invalid study appraisal instruments for assessing risk of bias. Okay, so we reject on that basis. We see that 60% of the time the submissions employ obviously flawed statistical or qualitative methods for synthesis. These are so obvious that I can tell. And then methods for certainty assessments, so more than 80% of the time, the submissions fail to assess the evidence according to defined set of criteria, right? So this presents a significant challenge, I think. If this is representative of systematic reviews across the board, we have a huge job in improving or moving the needle on how people are doing systematic reviews in our space, right? And then we have post-publication data, not yet in environmental health research, because we haven't looked at that, not aware of anyone doing a study of the quality of systematic reviews which have been published. But in medicine, we're pretty confident that 2/3 of the records in PubMed, which have been tagged as systematic review, aren't really systematic reviews. And then Matt Page and colleagues in 2016 found that most published systematic reviews have major flaws in conduct reporting still, and there'd only been a very marginal improvement in the quality of systematic reviews across the board over the preceding 10 years. Okay? Can we educate our way out of this challenge? I am skeptical that we actually can. I think that it would be a massive amount of effort over a 10 to 20-year period where we might get people doing environmental health systematic reviews about twice as well, say 2 or 3 times as often as they're doing it now, and it might still only be a quarter as often as we need. So, and that's using relatively simple current methods. If we start using complex tools like Robin-Z, which can only be applied by a very small number of scientists, there's a serious question about whether or not the methods that we are using, even at least the correct methods, are scalable or not. So we need a different approach, particularly when we think about the data volume problem that is implied in including mechanistic information into systematic reviews, where we've got many, many, many biokinetic events and event-event relationships which we need to analyze systematically. So the integration challenge, if you like, in a nutshell, is that if the stars align, simple systematic reviews can successfully be conducted. We know this because we see lots of them, right? It's the complicated ones that tend to struggle with, and it's increasing the proportion of successfully conducted systematic reviews, which is so challenging. So in most normal scenarios, systematic review methods are actually out of reach of most researchers' capacity to apply them successfully. Methods for integrating mechanistic data and systematic reviews are unlikely to be any easier to apply successfully. It's a much more complex analysis problem, and they kind of overwhelm us with data. The problem is, of course, that we can't just duck out of this challenge. Okay, the methods have to be applied in order for systematic reviews to be grounded. Okay, so we need a scalable approach to integration methods. So that would imply a computational approach, right? So basically, we need to turn features into numbers so we can make processes repeatable and scalable, so computers can start doing the drudge work for us, which are beyond, like, you know, the number of computations a small group of, say, 3 or 4 people can undertake over, like, you know, 2-year period, right? Algorithms are great because they give you discussable inputs, sort of modular inputs, which can be changed deliberately, so you can test different bits of the system. If you don't like, you can change it out for something else. We already do that with systematic review, in fact. It's just that we do that with people being in each of those places, and people take a long time to work, right? The challenge, of course, is preserving the links and the chain of evidence that keep the process grounded, right? So when computers are doing this stuff for us, they need to be referring to the text and referring to evidence that the interpretation they're making of that text is valid, right? So they need to respond to the same evidence that we would do if we knew about it, and they need to respond to the same features of the documents that we do when we're analyzing them. Otherwise, we end up with a black box thing. We don't really know what it's doing. So how do we do that for complex systematic review questions? Well, we can probably fairly easily turn judgments of similarity into numbers within our Pico framework, for example. Okay. We just do that using a Likert scale. So if we're asking a bunch of experts, we could just say, on a scale of 1 to 7, where 1 is same and 7 is different, what do you think about these different features of the Pico formulation, right? Then they might say, well, okay, so in this Ref 13, right, that's a human study, and our target population is humans. That's pretty similar. We'll give that a 1, okay? So we've got any adult against premenopausal women. So our observed study doesn't really quite match up with the desire of our target population, but it's not like miles off, so we kind of give that a 2. Well, they're looking at furans instead of organochlorine chemicals. That's quite a long way away, but maybe for this particular endpoint, it's not. They behave in a similar enough way that we can say, yeah, we could put some weight on that, but it's not completely irrelevant, so kind of middle-ish. And maybe like for timing or something, if we've got a population that's up to 16 years old, that's going to include girls who are going through puberty, so maybe that's not quite so directly relevant. We might want to file that under confounding instead. But we can at least see how we can turn a set of study characteristics into a matrix. And once it's in matrix form, we can start turning that into, we can start developing statistical descriptions of what that space looks like. Now, I'm not suggesting that we would use radar plots for this and do an eyeball test for assessing study similarity, but you can see if you describe your Pico statement as being kind of round, as 0 all the way around, then you can see how different studies or different Picos within that evidence space can have different shapes that you can compare to your desired target Pico. And if you did this kind of n-dimensionally and did it properly, that you'd start coming up with some quite interesting ways of describing similarity between study and target Pico, again, without having to go into this route of dividing evidence into streams and then recombining it later. The question is, of course, how do we ground these scores, right? What makes it correct that a rat is worth 3 in this scenario and that PRB expression is worth 4, right? It's a very good question. Grounding probably requires 3 big jobs to be done, right? We need systematic methods for AP development, we need automated data extraction, and we need machine learning models for weighting this sort of the characteristics of the evidence in this kind of evidence space, right? It looks like a big data challenge, ultimately. So systematic approaches to AP development, I think we're seeing this morning, so I'm not going to dwell on it, and loads of people know way more about this than I do. One of the things we do need to do is formalize the key features from which AOPs are built within a systematic framework, basically. So we need to know what information in the textual record we should be using when developing an AOP and get those rules really clear, right? And we need to know what rules we should be following when we're developing valid AOPs or determining their plausibility. That will need to be grounded, it will need to be systematic. But if we can figure that out, we know what rules the machines should be following, okay? Automated data extraction, well, we're looking at millions of documents there, and there are not enough PDRAs in the world to read all those documents for us. So we need to use machines to extract what will be a very large, very granular job across thousands of documents. At the moment, the natural language processing methods we have available aren't up to this task yet. They're quite good at titles and abstracts, but no one's developed a full text, a machine learning algorithm that can do this kind of data extraction from full scientific documents. And that's going to be necessary. There will be a corpus linguistics project, and it requires a full text toxicology corpus training set to teach the robots to read for us. Then finally, these machine learning models for weighting evidence. There's actually been tons of progress in this space in the last 5 years, and I think some people are starting to think that in 5 years' time, we could have made a really big step forward in this space. What is interesting is getting the machines to respond to the features of the evidence that we know affect reliability. So as far as I'm aware, in these large data models, there's a lot of numbers in there, but we don't necessarily know how reliable the experiments are that go feeding into those numbers. We don't really know if they're blinded or not, and we don't know how much blinding matters in those spaces. So these features need to be included. We can only include these features if we're able to put this data in from the narrative text that's in the original scientific studies that describe the methods that we use for developing that data. We can then use statistical models of those features to repeat human processes at high volumes. They can judge risk of bias for us and indirectness and all these things. Over time, once these data sets are big enough, the algorithms will identify features in that data set which if we knew about, because we were smart enough and could do that many computations, we would agree matter for predicting the toxicity of a chemical substance, and that would improve the performance of those big data approaches beyond human capacity. So just to conclude, successful evidence integration requires us to ground complex judgments of the directness of evidence in the textual record of research and in biological knowledge. We've proposed a framework for using Pico statements to structure judgment about external validity, which seem to necessitate a computational implementation and take us away from stream-based approaches to evidence integration. And I think that to some extent we've outlined a research roadmap toward how such an implementation can be realized and grounded. I'd like to thank my colleagues at Lancaster, particularly EBT staff as well, and Rebecca Morgan and Michelle Anguish, who've heard this presentation 90 million times. And I'd like to thank you all for listening.
Thank you, Paul. We started a couple of minutes late, so we can have one quick question, and then we'll have the rest of them at the panel discussion. Please, Michelle.
Not even a quick question, but a quick comment in that.
Introduce yourself, please.
Michelle Anguish, US EPA, IRIS. So that, you mentioned bringing out these features and extracting them using annotation and NLP and so forth. And I think that it's really important to remember that as we're extracting this stuff, we need to make sure that we're maintaining the original context. So we need to make sure we know what animal it's coming in. We need to know if it's a biomarker or a gene expression marker or whatnot, because if we lose context, then we lose a lot of meaning as well surrounding that data.
Yeah, that's why it's a tough job. Yeah. So, given. It's a fox-bodied bat. Sorry, it's a bat-eared fox. I just call it a fox-bodied bat because I'm an idiot. So I start classification of the ears. Sorry, it's a bat-eared fox because I think I'm funny. I called it a fox-bodied bat because I start my animal classifications from the ears down.
Thank you, Paul.